Chapter 3: Electric current in environments. Electronic circuit is assembled with third combinatorial circuits. In the history of mankind, each development period is marked with a typical kind of material. We experience the Stone Age, Bronze Age, and Iron Age. But now, it is difficult to state a material specific for modern civilization. To serve the electronics industry, people have not only taken advantages of all available materials in nature, but they are also trying to design and manufacture materials according to their requirements. So, we need to find out characteristics of electric current in different environments to be able to understand the basic principles of modern technologies. This chapter mentions electric current in environments, starting by the research of electric current in metal, then research of detailed features of current in electrolytes, gases, vacuum, and semiconductors, and mentions the corresponding applications. Unit 13. Electric current in metals. In the previous units, we said that electric current in metals is a flow of electrons moving in direction. But like all other materials, metals are also formed by linking atoms together. An atom consists of a positive charged nucleus and negative charged electrons rotating around. So what characteristics do electrons in metals have, and how do they govern the properties of electric current in metals? That is the content of this unit. First Roman, the nature of electric current in metals. Figure 13.1. The crystal lattice formed by positive ions is arranged in an orderly manner and free electrons move chaotically in the lattice. The nature of electric current in metals is stated clearly in a general theory called electron theory of electrical conductivity of metals. That theory has contents as follows. 1. In metals, atoms' lost valence electrons become positive ions, figure 13.1. Positive ions link in an orderly manner, creating a metal crystal lattice. The thermal motion of ions, the oscillation of ions around the equilibrium position, can destroy this order. The higher the temperature is, the stronger the thermal oscillation is, the more disorderly the crystal lattice is. The crystal lattice cell of copper metal. Two valence ions are separated from an atom, becoming free electrons with a constant density n equals constant. They move chaotically, creating free electron gas and occupying the whole volume of the metal block and don't produce any electric current. 3. The electric field E, produced by the external power supply, pushes the electron gas to float in the opposite direction with the electric field, creating electric current. 4. The disorder of the crystal lattice obstructs the motion of free electrons, which is the cause of metallic resistance. Common disorders are the thermal motion, thermal oscillation, of ions in a crystal lattice, the distortion of crystal lattice caused by the mechanical distortion and strange molecules in a metal. The resistances of metals are very sensitive to these factors. The electron theory of electrical conductivity of metals shows that charged particles in metals are free electrons. Their density is very high, so metals are very good conductors, Table 13.1. Many different properties of electric current in metals can also be deduced from this theory. In this table, silicon isn't a metal. Its resistivity is greater than the one of metals by several orders. So, currents in metals are the directed displacement direct of free electrons under the impact of the electric field. So, currents in metals are the directed displacement direct of free electrons under the impact of the electric field. 2 Romans, the dependence of resistivity of metals under the temperature. When the temperature rises, the thermal motion of ions in the crystal lattice increases, making the resistance of metals increases. The experiment shows that the resistivity, ρ, of metals increases under the approximate temperature by first-order function. Equals 0 1 plus alpha, Tt0. Where 0 is the resistivity at T0 degrees C, commonly 20 degrees Celsius, A is the coefficient of thermal resistance with the unit of K-1. The values of 0 and A of some metals are listed in Table 13.1. The variation of resistivity of copper under the temperature. However, if making an exact experiment, we will see that the coefficient of thermal resistance of each metal does not only depends on the temperature, but it also depends on the cleanness and processing mode of that material. Nowadays, the coefficient of thermal resistance of platinum has been researched very carefully, because people use platinum commonly as thermometers for industrial use. C1. C1. Why do people choose platinum wire to make resistance thermometer for industrial use? 3rd Roman, the resistance of metals at low temperatures and the phenomenon of superconductivity. When the less the temperature is, the less disorderly the crystal lattice is, so the less its resistance to the motion of electrons is, the metal resistivity decreases continuously. Near 0 K, absolute zero, resistances of clean metals are very small. The graph expresses the resistivity of copper under the temperature is drawn as shown in figure 13.2. Table 13.2 The critical temperature of some superconductors. C2 at some metals such as Hg, Pb, etc., or some alloys such as Nb3Sn, Nb3Ge, etc., and some ceramic metal oxides like DYBA2Cu3O7, when the temperature is lower than a critical temperature Tc, the resistivity suddenly decreases to 0. The critical temperatures of some matters are listed in Table 13.2. Many other properties such as magnetism and capacitance also change suddenly at this temperature. We say that those materials have changed into the superconducting state. Nowadays, superconducting coils are used to create magnetic fields that normal electric magnets cannot create. Let electric current flow through superconducting coils, then remove the power supply, the current still continues to run for many years without weakness. In the future, it is expected that superconducting coils can be used to transmit electricity, and energy loss is no longer on lines. C2. C2 Why can the electric current in a superconducting coil without a power supply be maintained for a long time? Can we use that current for machines to operate forever? 4th Romans, phenomenon of thermoelectricity. Electrons diffuse from the hot end to the cold end, making the hot end charged positively. The electron theory of conductivity of metals also shows that if a metal wire has a hot end and a cold end, the thermal motion of electrons will make a part of free electrons at the hot end concentrate on the cold end. The hot end will be charged positively and the cold end will be charged negatively. Figure 13.3. Copper, constant and couple. The temperature of the burning candle T1. The temperature of the melting ice T2. T2 equals 273 K, 00 C, 0 degrees centigrade. Voltmeter, thermal electromotive force E, copper wire, Konstantin wire, ice water, burning candle. Between the hot end and the cold end there is a certain voltage. If we take two different metal wires and weld their two ends with one welded joint kept at a high temperature, another joint kept at low temperature, the voltage between the hot end and the cold end of each wire isn't the same, making an electromotive force in the circuit. Figure 13.4. E is called thermal electromotive force and the set of two conductors welding their two ends is called thermoelectric couple. Experiments show that E equals alpha T, T1, T2. Where T1 T2 is the temperature between difference at the hot end and the cold end, alpha T is the thermodynamic coefficient depending on the nature of two kinds of materials used as thermoelectric couple with the unit of Vk. Although the thermal electromotive force is small, it is very stable over time and experimental conditions, so thermoelectric couples are commonly used to measure temperature. Three commonly used thermoelectric couples are platinum, rhodium mixed platinum couple with alpha T, similar, 4,41V/K. Chromen alumen couple with alpha T, similar, 4,41V/K. Copper, Konstantin couple with alpha T, similar, 40V/K. Summary. Charged particles in metals are free electrons. Their density is very high, so metals are very good conductors. Electric current in metals is the directed displacement current of free electrons under the impact of the electric field. The thermal motion of crystal lattices obstruct the motion of charged particles, making the resistance of metal depend on the temperature. Near 0 K, absolute zero, the resistance of metal is very small. Superconducting materials have resistances decreasing suddenly to zero when the temperature TTC. A thermoelectric couple consists of different metal wire with two ends welded together. When the temperatures of two welded joints T1, T2, are different, there is an thermal electromotive force E equals alpha T, T1, T2, in the circuit with alpha T is the thermoelectric dynamic coefficient. The end.